It is my honor and pleasure to present Klesta Qehaja. She will be talking to us about random walks. So please.
Right. Mathematician George Qehaja liked to take walks through the woods to calm his mind, and he noticed that he would always bump into the same couple, and this got him thinking that what are the odds that he would bump into the same couple every time. So to understand this, we are going to have to do with random walks. So first, what is a random walk? A random walk is a very general type of a random process. It always involves taking a series of steps, and the direction of those steps is determined probabilistically. So to get the basic understanding of what random walks are, I'm going to start by explaining a simple random walk on the integer line. So say we take a coin and we flip it. And so we know that the probability that we get heads is 1/2, and the probability that we get tails is also 1/2. And say if we get heads, we move 1 to the right, and we get tails, we move 1 to the left. Then with 1/2 probability, we're going to be standing at the number 1, and with 1/2 probability, we're going to be standing at -1. After 2 turns, the probability that we are going to be standing at 0 is 1/2, and the probability that we are going to be standing at 2 or -2 is going to be 1/4. If we do the same for 3 and 4 terms, we notice we're going to get an interesting observation that first, on the odd terms, the random walk can only be on odd numbers, and on the even terms, it can only be on even numbers. And second, as the number of steps increases, the probability distribution of the walker's position begins to resemble a bell curve centered around the origin. A formal definition of this would be, let xn represent the position of the walker after n steps. At each step, the walker moves either +1 to the right or -1 to the left with equal probability 1/2. The position after n steps is given by the following formula, and where fi is the outcome of the ith step. So fi can have either a value of +1 or a value of -1, and x start is the starting position. So to understand the random walk on 2D, the walker simply moves on a grid with 4 possible directions at each step, being up, down, left, and right, and each direction is equally likely with the probability of 1/4. And similarly for this is not okay. And similarly for a random walk on 3D, the walker has 6 possible directions at each step, that being up, down, left, right, forward, or backward. And again, each direction is equally likely with a probability of 1/6. Maybe I don't know how to use this.
Click on the cursor.
To the,
Too much.
Just skip something. Okay. So a more general definition of a random walk would be to let x1, x2, etc. be a sequence of independent and identically distributed random variables. And a random walk that starts at z is the sequence where s0 is equal to z and is described by the following formula. And the random variables xn are called the steps of the random walk. Something notable about this is the independence. So each step xn is unaffected by the previous steps, and the identical distribution. So all steps share the same probability law. So random walks on 2D and 3D. I would like to continue with the famous quote on this topic. It's that a drunk man will always find his way home, but a drunk bird may get lost forever. We will see this now. The assumption here is that a drunk man walks on a 2D random walk, and the drunk bird, presumably we get the drunk bird, walks on a 3D random walk. The difference is obviously 2D and 3D, though it also has a unique characteristic, is that the drunk man is guaranteed a return and the drunk bird is not guaranteed a return. This gets us to recurrence and transience. Let V be the number of visits to the origin. We define recurrence to be a random walk is recurrent if the probability of the return to the origin is 1, or the expected value is infinite. And we define a random walk to be transient if the probability of returning to the origin is -1, so it's not guaranteed, and the expected value of returns is less than infinity. For example, for a 3D random walk, the return probability is 0.3405, also known as Polyot constant. Also, we can notice that it's less than 1, so it's not guaranteed. A general schema for the proof would be an overview is that first, the probability of return is 1, and that's the same as the expected value being infinite. Second, the expected value is equal to the sum of p to n, starting at n to infinity, where p is the expected value to return to a center point after 2n steps. And then it's finding p to n, and it's given by that formula. So multiplying 1/2 to the 2n by the number of paths, and also finding the number of paths. Also, this step is a computation for a one-dimensional walk. A proof sketch. The expected value is 1 times the probability of b being 1 plus 2 times the probability of b being 2 times 3, etc. To make the calculations easier, we can rewrite this. And if we look at the columns, we will notice that the first column is the probability of v being bigger than 1. And the second column is p, the probability of v being bigger than 2, and etc. We can rewrite this as a sum. And we say that r is the probability that the walker returns to the origin at least once. And if we simply rewrite this, we get r plus r squared plus etc. And we know that this is r over 1 minus r if r is in between 0 and 1, as probability should be, and it's infinity if r is 1. And in our case, we want it to be infinite, so r is equal to 1. We also have a proof sketch for the one-dimensional. That is the general formula for the 1D. It's 1/2 to the tn times the 2n times the number of paths, where the number of paths is determined by the dimension we are talking about. So for example, in one dimension, to return to the origin, if you start from the origin, you need to travel the same amount to the right as to the left. And we are looking at the case in which a random walker returns to the origin in 2n steps. This happens when the total number of rights and lefts are the same. So the combinations for this would be 2n choose n. And then, again, we have the same formula. And using this, we can calculate p to n. And we get an approximation that it's 1/n. When we take the limit, it's 1/n to the 1/2. And its sum is infinite. The same happens for 2D. The sum is, again, infinite. But the same doesn't happen for 3D, which shows that in 3D it's transient, and in 1D and 2D it's recurrent. So for just to see what the formulas would look like for 2D, this is how you would find the number of return paths and how you would find the probability. And for 3D, again, this is the formula for 3D. And now we have the applications of random walks. I chose to talk about the application of a random walk in finance. The first is the efficient market hypothesis, or EMH. The efficient market hypothesis asserts that financial markets rapidly incorporate all available information, making future price movements incoherently unpredictable. This concept aligns with the mathematical framework of random walks. So the random walk hypothesis says that stock prices behave like a discrete random walk, where each price change is independent and identically distributed. This mirrors the EMH's claim that prices adjust instantaneously to new information. And the empirical evidence or studies of stock returns often show that statistical properties, for example, negligible autocorrelation or fat tail distributions, are consistent with a random walk. And then, we have two images. The first is a simulated symmetric random walk, where the path exhibits no predictable trend. And the second is a historical S&P 500 price movement. And we can note the similarities to A, but with volatility clustering. Here are some references that I did based on to do this. Yeah.
Yeah, we're gonna see if
Do you have
anyone has questions for the speaker.
Yes.
Yes, so I guess you can't really move the slides, but on one of the slides, you showed the picture for 2D random walk, and the starting point was different from the origin. So, like in the so yeah, in this case, it's a bit different from when you were trying to find out the probability of returning to your starting point. So, like, these are a bit different problems. If you're going to return to the same point you started at, and if you're going to return to some home point which is different from the starting point, so are these problems equivalent or not?
Finding the probability of whether returning to the origin from whether you started at the origin or whether you start away from the origin, right?
Yeah. So.
It is proven that no matter where you start, you will always. It's the same as if you started on the origin in 1 and 2D.
Into the.
Yeah.
Okay. Yeah.
It has to deal with the fact that we can always transform the grid line into something else using some appointment solution.
No, I think
I don't think it's.
so here, if we have guaranteed return to the home, then we can just skip first finite number of steps.
Yeah.
Just start counting from it.
Okay, but I guess then in 3D,
Yes,
the probability would be different depending.
Yes,
Yeah.
because it's smaller than one.
Yeah. So the Polya constant is probably then for the starting point being the origin.
Yes.
Yeah. Okay.
I think in this case, both of the events, if we start from a different point and if we start from home, all of them should come into the tail signal, right? Because you can remove finitely many steps, and that will still converging. So it's like when we look at a conversion sequence, no matter how if we remove finitely many points, it does not change the fact that our system still converges to that particular.
Okay. Yeah. And could you move to the last slide? So I have another question. Yeah. So you didn't really explain what volatility clustering is and what's like the connection between these two. Yes.
Well, this is based on the random walk hypothesis. Stock prices behave like a discrete random walk. And here I just compared a simulated random walk to what price movements like.
Okay. Yeah, but well, first, I guess just some random walk would usually be a bit different from the shape of the specific price movements. But I was asking about what you mean by volatility clustering.
Yeah.
Okay, so what's
So, good question.
Yeah, I think the idea was more to show the qualitative.
Yeah.
so that is just looks like
Just
an
similar
actual
trend.
random walk.
Yeah,
So-
exactly.
So is there like just some measure of the randomness of the walk? So is there a way to actually somehow see if this just like if it just looks like a random walk or if it's really more random than anything else?
Isn't that still an open question?
I mean, yeah, and I guess like counter theories to it in finance, because you have that like the random walk theory, but you have others that would say something different.
No, I was asking a bit different questions. So
Is there some way to
like a more statistical question. So if you have a specific data about price movements, so you verify if this is probably remote or not.
I don't know, maybe. I mean, there can be some quantifier that says how random a system is, right? Because we can immediately look at a straight line and say, okay, this is not random, and we can see these kind of second lines and say, okay, this probably is random.
Very good. I wanted to know if there are more questions for the speaker.
Yeah. Based on like this like random walk theory that you talked about in terms of in finance, does it always assume like a simple like symmetric random walk when it comes like to predicting these prices? Like, and what I mean by that is like basically does it always like assume that the prices like rise in or that they will like as often as they fall, or do you have like specific tendency that it
Specific tendency in random walks that it will tend towards zero. It's a bell curve.
and this is would be the same case here applied like in stocks? Like, you would assume what exactly would be the assumption then here?
I think what she's trying to ask is if we can have some biased random walk such that kind of mimics the behavior you would see in
Sort of, yeah, I mean.
Yes, you can have a kind of biased random walk where the probability is not like, oh, it's half-half. It could be 0.6 for right or 0.4. So it can be biased. I think.
Okay, so more questions for the speaker.
I have one small doubt. In the diagram, can you please go back to the diagram with the
Diagram.
in the back, further in the beginning?
The
Yeah, the part,
path, okay, this one.
not this one, the one before this, the 3D, 2D diagram. Yeah, this is a very curious diagram because, I mean, I'm not really good at math. I'm just based on the visual that we're seeing here. So if I were to like say there's infinite ways that I can move in like 3D, so that's gonna be basically me going from here to there is gonna be 0, right? Because it's 1 over infinity. That, I don't know how that would that be the case.
So I think what he's trying to say is that he's thinking of a random walk that doesn't take discrete steps, basically. So the random walk you're
It's just
talking
any
about,
arbitrary direction.
yeah. Well, this is a random walk on Z cubed, correct?
Yeah.
So
So if I were to walk in any direction given in 3D space, probability that I go from here to there would be 0, right? Because there's infinite ways that I can sort of
yes, if you are doing a random walk on R cubed,
Cubed?
R.
When is even R squared?
That field like continuous, so not step.
Yeah, exactly. Like in a continuous plane, also discrete.
Yeah, but then it will be a random process. It's just separate topic that is studied
Okay.
apart from the probability theory. But yes, such theory exists. Usually, it's studied by some frequency analysis.
Yeah.
No
The
idea.
difference here is that we're in the lattice, the two-dimensional lattice. So we're only moving to integer coordinate.
Okay.
So with this, I would like to thank the speaker once again.